So the first presentation this afternoon will be by Jackie, who we already know from the morning, on TTM paths specifying and verifying time transition models.
Good afternoon. This talk is going to be about introducing a tool called TTM/path. TTM standing for Time Transition Models, and path standing for the framework of process analysis toolkit. And I'm actually going to show you how we actually introduce a new modeling notation, which is expressive and convenient for modeling reactive system. And we also have automated tool support for simulation, model checking, and static type checking, etc. And we also have some case studies to show you. This is a joint collaboration with Liu Yan and Sun Zheng from Singapore. They actually have contributed a lot to the implementation framework, but they're not here yet, so I cannot say hello in the audience. Anyway, so what's the background about time transition models? So TTMs are a guarded transition system for describing reactive system, where in the transitions you actually have time constraints, either on timers or on the time bounds of the events. I will actually show you an example of what I really mean by that. And the TTMs has been reported in a journal paper, which we cited in our current workshop paper, that the TTM has been used to specify a nuclear reactor shutdown system, and it has been used to validate the requirements of the shutdown system. And what they did was to do a manual encoding from the TTMs into the foreign language like Uppaal and SAL model checkers. So they actually translate TTMs into time automata and model check it by Uppaal, or they actually translate TTMs manually into SAL and then into time transition system and then model check it by SAL. That's what they have done in the literature. We don't think manual translation is the way to go, because you really want to automate the translation process for your TTMs such that you can really try to get rid of the unnecessary transitions or states that might result from your manual encoding. I'll show you statistics to prove my point. So the main selling point about this paper is really the modeling notation. So we actually provide a textual syntax for the TTM's notation, where we actually have discrete time domain interpretation of the system. So in that case, we have a tick event, which we can refer to in our properties verification. And we also specify the system as a parallel composition as module instances. And we also have local and global timers, which we can use in the time transitions. We also have mnemonic or non-deterministic assignments to actually model an arbitrary environment to say, given this typing constraint for your environment, it can do whatever it likes within that typing constraint. I'll show you how this can be done to support compositional reasoning. That's sort of the extended work beyond this paper. Also, we have, at the event level, we actually support time bounds, and we also support fairness constraint. You can actually specify to say, for my event, what should be the fairness assumption I would like to impose? Whether should that be no assumption, or should that be weak fair, or strong fair? We also support the LTL properties language, where you can actually verify both untimed and timed properties. We can also refer to the tick transitions or the occurrences of any events in your LTL formula. I'll show you an example in the case study. Okay, and other than that, we also have some automated tool support in the PAT framework. And so, two main contributions: modeling notation and automated tool support in the PAT. So, a very general overview of the PAT, TTM PAT architecture. So basically, this diagram was taken from the PAT website. The only thing I changed was to add this box over here. So now we actually have a domain-specific plugin called TTM on top of PAT. The labor required was to actually have some domain-specific abstraction to actually define what should how should you make transitions in your time transition models. And the corresponding semantics we developed is actually the LTS, label transition system. So it's actually an explicit state representation, so which is not the most efficient way we might go. So for future work, we may want to improve this encoding to support a better model checking performance, like a symbolic model checking. But that's not the focus of this paper, not yet. So for your model check, before you model check, you may want to do some visual simulation based on your LTS semantics. And you can also do verification. And the good thing about this tool, TTM Pad, is if you got any counterexample from your safety property or liveness property, you can actually generate the counterexample. Let's say for liveness property, you can actually identify the loop within which an infinite number of the loops would not actually satisfy your liveness property. And you can actually trace back from the counterexample back to the original model. I'll show you what it meant. So that's sort of the general architecture. So this is the path that we're currently following. So we are hoping to get to the binary decision diagram or some difference bound matrix as a future work. Okay, so we have maintained a resources page for the TTM path, and where we actually get installation instruction, we get the precise grammar, and we have a tutorial video there, also produced by me there, but it's a different context actually than this talk, just to show you how you can do TTM modeling, for a reactive system. We also have most importantly for this paper, if you're interested in our experiments and would like to reproduce them, we also have an experiment to actually give you all the raw data and to give you the more detailed statistics than what's presented in the paper. Okay, so this is a summary of our contributions. There are three main contributions. First is mainly the textual syntax we are trying to support, and which was not supported before in the literature. And we also have an operational semantics of the TTMs using LTS, which make it amendable to automated tool support. And the third contribution is we also have tool support in PET. And our performance evaluation shows that our performance is significantly better than the manual encoding in Uppaal. Not to say we are better than Uppaal, but just to say the manual encoding that's available in the literature, we are far better than them. Okay, I'll show you the statistics later. Okay, let's consider a small example or realistic example, a pacemaker. So a pacemaker is an electronic device implanted into the body to both to detect the natural heartbeat and to regulate the heartbeat by delivering some electrical stimuli in case if your heartbeat doesn't really occur beyond a certain amount of time. So that's the pacemaker. That's how you actually implant it physically into the heart. So that's the example we're trying to model. Okay, so this slide summarizes the VVI mode of the pacemaker, which is the natural language description of what a pacemaker should do. Let's just go over them very quickly. So first of all, I want to draw your attention to three constants. The first one is the hysteresis rate interval, and the second one is the lower rate interval, LRI, and also the ventricular refractory period, VRP. So these are the three constants we're going to play around in the model. So let's go over them very. Okay, well, that's fine. Yeah. Let's go over it very quickly, the slide. I'll read it with you. So basically, we want to know what's the default maximum time between two consecutive sensing of the heartbeats. By default, it is actually the larger value of the hysteresis rate interval, assuming that your heart is normal. Now we have two cases to decide for each timing cycle. Either a heartbeat is sensed, or the heartbeat has not occurred within that default timing interval. In case it has not occurred, we have to set a pace to the heart, and we have to set the timing cycle into a smaller number, because now that we have detected that the heart is not really normal, so we have to make sure we look after it more frequently. And the other case is we actually have sensed the heartbeat. So in this case, if we previously set it to be LRI, we now have to set it back to HRI. That's basically the logic we're playing. Okay, that's a natural language description. So this is sort of the state diagram for the heart and the controller. It's not very complicated. So basically, this is the heart on the left, and this is the controller. So the heart, oh, by the way, there's one thing I should mention in the previous slide. And every time before the controller can start to sense, the controller has to make sure to avoid all the possible noise that results from the electronic signal. So that's something we have to take care of, which is the VRP, which means the controller has to wait for VRP time units before we can start sensing the heartbeat. Okay? Having said that, let's have a look at the high-level state diagram, and we'll show how to translate this. What's the TTM counterparts for these two state diagrams? So the heart may either, so HBN standing for heartbeat natural and heartbeat paced. And this is to sense and this is to pace. So what the heart can do is to either to beat naturally or to beat forced by the controller, either way. And we actually have two shared variables to kind of simulate the channel synchronization, because at the moment we don't actually have channel synchronizations in our syntax. We're trying to support that in the future release. But for now, we just want to show you can also do that somehow in TTM. So we have two global variables. One is sense, the other one is pace. The heart, as soon as the heart actually set the sense to be true, which means it's a natural heartbeat, which has just occurred, the controller event is going to actually read it and set it back to the default. So that's like a channel synchronization. You can see that for each event, at the event level, we actually have the time bounds for the event. In this case, it says 00, which means it's an instantaneous event. As soon as there's a heartbeat, the controller can know immediately. In this case, and similarly for the pace heartbeat and for the other two events. Let's just go on. Let's just have a look how we actually do this in the TTM syntax. So first of all, we can define the semantics for the three, we can define the value for three constants, and we also declare a timer for us to do the verification. I'll show you how we do that. So timer value actually go from 0 up to the hysteresis rate interval +1. We use the +1 here just to make sure we never reaches +1. We're always bounded by HRI. And we also have two shared variables, as I showed you before, sense and pace. Okay, so this is the module for heart, which is the environment for the controller. And we actually have two variables declared to be shared. So we actually have three kinds of modifiers for variables. It can be in, it can be out, it can be shared. In means you cannot change it from your current module. Out means you are the only module in the system that can change their variables. Share means anyone else can change it or read it. And we also have the difference between interface and local variable, which has the obvious meaning. One is global, the other one is local. And here we define some auxiliary variable just to capture the old value for the rate interval. And we also have the program counter, because in the event-based system for TTM, we actually don't have the explicit control flow, which we think is a more abstract way and high-level way to specify the system, as opposed to some process algebra like CSP or time automata. And here, this program counter is actually how we encode the sequential flow, if you like, to encode it. Okay, let's have a look very closely on this particular event just to learn the syntax. So for the events, as I said before, you actually have the lower time bound and upper time bound here, and you also have the when specifying the guard of the events, which means, I'll just draw some diagram for you to understand. Imagine this is time, and this is the guard for the events. As soon as the guard of the events becomes true, you will have to wait. In that case, it's between VRP. Let's just to make it more general. So let's say we have lower time bound L. You have to wait this amount of time. And in that interval, the guard has to continuously remain true. Otherwise, you will recount your logic. And after that, you have the upper time bound U minus L. And within this time interval, the event must be taken. Otherwise, the time will just stop. That's actually how we encode the semantics for the events. For detailed semantics, you can refer to the paper. I'm not going to talk about the details in this talk. Okay, so we have the lower time bound, we have upper time bound, we have the comma here. So the way we do the assignments are parallel assignments, so they are not sequential. So here you see we assign Ri to be HRI, and here less Ri to be Ri. So this Ri here denotes the initial value. It's like a pre-state value for this variable. So it's not really the updated value of HRI, just some detail about the updates. And we have guards, and we have timers. So in this case, we're saying whenever we are trying to start a new cycle in the heart, we will actually start a new timer to recounting the timer value. Okay, that's also for the verification purpose for us to specify properties. Okay, similarly, we have the electrical controller module. So we have interface, we have local events, etc. So they correspond to the behavior I just explained, the state diagrams. So they are not too much surprise. So once we have defined the modules, there are two things we have to do. First, we have to instantiate the module by binding the input and output variables or shared variables. And the second thing to do is to put them in parallel. You can choose to put the heart alone. Just you can say the system contains just one single heart without a controller. You can see how that behavior looks like. Or you can actually have the regulated heart by putting that in parallel with the ventricle controller, either way. We also support the iterated composition. For example, in the Fisher's algorithm, you can actually say, given the process ID I, ranging from 1 to n, we can actually pass I over here as the arguments. We also do the corresponding binding for the variables and for the process. We can also do that. It's like index parallel. Okay. So far we have showing very quickly the syntax of specifying the system. Now we should look at how we specify properties. What channel do I have? Okay. 7. Okay, thank you. Okay, so for the properties language, this is actually a comparison between the TTM. We actually use the LTL, linear time temporal logic, for TTM test. We have the TCTL of the Uppaal. So this is actually a detailed comparison of what they can express in the properties. The detailed explanation is actually in the paper. I just want to draw your attention to a few things that we can do, but Uppaal cannot do. So we can directly verify the non-standard behavior, which means because we might have instantaneous events, which means time might just stop at some point, but we don't want that to happen because time should always go on. So we should say infinitely often, the time will always proceed. And we also support until and release operator, which was not supported in Uppaal. We can also nest the temporal operators, and we can also refer to the occurrences of events. I will show you the example, but our semantics actually supports to the transformation from event occurrences into state predicates, so they can be checked in the LTL. And this is also one novel feature of our language, which is whenever you have a timer to be specified in your property, you can actually say, has the timer been monotonically increasing on this value without being reset by any other events? This is actually a very useful thing to have in your verification. I'll give you one example in the next few slides. Okay, yeah. That's the comparison for the more details. Please refer to the paper. Okay, so this is, I just want to talk about just one formalization of the requirements. So this is to say, so here you can say, the system actually satisfies some property here. Henceforth, this is an implication here. The antecedent says, whenever there's a new cycle, so this is an event, so we are referring to occurrence of an event in the formula. Whenever a new cycle of the heart occurs, then the following actually happens. Okay? And this part here is actually an until operator. We are trying to say between the new cycle, the beginning of the new cycle, and the occurrence of a natural heartbeat or the pace heartbeat, the timer must be monotonically increasing without being reset. Otherwise, if you can just arbitrarily reset your timer, then you can very easily make this formula true. Okay, that's the kind of the motivation. And we want to say, in that case, the timer is always within the range of the two constants. That's the big picture. Okay, so as I said, we can check non-signal behavior, and we can also check some safety properties. Okay, let me just show you very quickly that. So this is the TTM Path tool. I just want to show you that we actually have got a small library of examples. Once you install the tool, you can actually try out all the examples. The pacemaker example is exactly here, which you can try out. Okay, let me just go back to the slides. So just a few features in terms of screenshots. So we have some static type checking for your syntax. If you refer to the wrong event name, we can catch that. And also we can generate a reachability graph from the simulation node. So this is the whole reachability graph for the pacemaker. And we can also do manual simulation from the graphical interface. And you can actually always see what's the current states for your trace. And also what are the events that are also available at the moment for the current states. And we can do verification and also show some statistics about how many states you have visited, how many transitions, etc. In case you have a liveness property violation, let's say, so this part that's highlighted identifies the loop where the liveness property doesn't really satisfy. And if you click on that, say, simulate with this trace, you can actually go back to the original simulation node. It has all the state information there for you to actually debug your model. It's a very handy tool to have, really. Okay, now I just wanted to say something very quickly about the case study. So the case study we did was actually a slice from a production nuclear reactor shutdown system that has been previously published, and we are actually using the same model, and we are trying to use it to specify it in TTM. So we have a nuclear reactor, we have the shutdown system controller. The controller is going to read in the pressure and power of the reactor, and the controller is going to decide whether the controller should open the relay and shut down the reactor. And that's the high-level description of the controller, and that's sort of the analog implementation for the controller. Let's just have a very quick look at this. When the pressure and power simultaneously go above the set points, we have to count some time and then we check again. If after that time power is still high, then we have to open the relay. Okay, and then we have to just do another check to see if the power actually goes back to normal. Then we have to recover from the open relay. That's kind of the logic we are trying to do. Okay, and this is sort of the two properties that we verify. So one is liveness property, and the other one is the safety property, and both of them actually involve some timing constraints. For the details, please refer to the paper. And this is the statistics. So I just want to draw your attention to this one. So this one where we actually have, so this is an encoding in Uppaal. This is our TTM path model. We have much less number of states and transitions than the Uppaal encoding. So this suggests two things. First, our automated translation is actually much more efficient than the manual translation for the Uppaal. And second, even though the Uppaal tool actually has this many transitions and states, they are not that much slower than us. So that really suggests we have to later on improve our performance. But at the moment, we are still the strongest in terms of encoding. We are best. Okay, so there are actually more details about the semantics in the paper, which I won't touch. So I have said pretty much all the modeling features I want to say. And final slide is about the extended work that we're doing in some extended document, which is to do compositional reasoning. So somehow we want to say, if we can verify module 1 with respect to some arbitrary environments, then module 2 with respect to some arbitrary environments, and if we can somehow discharge the proof obligation that P and Q implies R, then we can certainly derive that putting them in parallel will satisfy R. So this part, so these two will be done in model checking, this one will be done in theory proving. And we do have the syntax support for that, so we have the mnemonic assignments to say power can be anywhere in the state type, which is on, high or low. And also the pressure is high or low. That's our syntactic support. Final conclusion, so 3 contributions. Textual syntax for the TTM notation. We have also the semantics, which is detailed in the paper. And we also have the tool support in the path framework. And we also perform significantly better than the manual encodings in Uppaal and SAL, as I showed you. However, we intend to improve the performance with collaboration with our Singapore colleagues, just to use some optimization techniques. Yeah, and also our event-based syntax is also amenable to theory proving. If you're familiar with the event-based notation, we can actually generate proof obligations for the proofs. But the model check is rather undistinct. Okay. This is just some further reference for the compositional reasoning. We start coming down. Thank you.
Thank you. Any questions? You have a few minutes for questions. Yes?
Yeah.
How do you compare with, so in terms of expressiveness and maybe usability, how do you compare with statistical activity, which is also improved in fact?
Well, okay, let me just go back to the well, certainly the paradigm is actually different because in FTSCS'13 they use the process algebraic notation, they use the event-based notation. Let me just go back to that table there. So, just give you some examples for detailed comparison, we can take out one. So to actually check the non-settled behavior, they cannot do that in stable-defined CSV because they cannot directly refer to the peak transition in the LTL formula. So they can do basically everything we can do except here, also the monotonicity of timers, they also cannot do that. Yeah. Also, but again, it's a different modeling paradigm. So in their case, the control flow is explicit. In our case, we simply just structure our updates into events as opposed to state diagram.
Other questions? I have one question. Did you choose the tools after manually translating some examples and comparing the performance, or did you do this manual translation to Uppaal later on?
Oh, sure. I should really clarify this. So we compare the TTM, and we compare the Uppaal, we compare the SAL. The Uppaal and SAL were done previously by our colleagues. They actually did a manual translation into Uppaal and SAL. The only difference is we took the same model, but we ran it with the most up-to-date verification engine for Uppaal and SAL. And we found that their manual encoding was simply not satisfactory.
Okay. Let's thank the speaker.